let's get started. So this week there's 4 questions on the problem set, and some of them might be a bit long, so we have quite a bit of material to cover. So let me just get started. The first 2 questions I'm not going to spend much time on. They're pretty easy. We did a lot of it in class. And number 3 and number 4 are, I'll give you some hints on that. So just quickly, number 1, you're dealing with a van der Pol oscillator. So you have something like double dot. Okay. Something like this. So Professor Rock described how you would turn this into a linear part plus a nonlinear part in class, but just in case you missed the video on Friday because the quality wasn't great, let me just quickly do that again. So first you expand it out. So we have here is the linear part and here is the nonlinear part. And what we're looking for when we're doing this is we're looking for the limit cycles. And if you consider just the normal closed loop block diagram, let's say this is R and this is Y. So the loop gain, the closed loop transfer function is going to be NL over 1 plus NL. And when we're looking for limit cycles, we're looking for neutral stability. So that means the poles of the closed loop transfer function essentially go to 0. So we're looking for the solution to the equation 1 plus NL equals 0. What we can do now is, let's say that we define NL as some rational expression consisting of a numerator and a denominator. Then if we sub this into the equation, we have, and just expand it out, we have denominator plus numerator is 0. So then what we said was, let's let the nonlinear part be the numerator, and let's let the linear part over here be 1 over the denominator. So essentially what we're saying is this part is going to be the denominator, this part is going to be the numerator. And we end up with n is x squared x dot, and L is 1 over x double dot minus x dot plus x. So once we have this formulation, we need to find the describing function for this nonlinearity. And in class we showed that the describing function for this is a squared over 4 with an angle of 90 degrees. So you should verify this and work it out in your homework. And once you have this, all you have to do is plug this n and L into this equation and just solve for A and omega. So this will become a complex polynomial expression, essentially, of 2 variables, and I believe it's pretty easy to solve. And you're looking for, if there are multiple solutions, you're looking for the positive and real solutions for both A and omega. So that should be pretty straightforward. That's all I'm going to say about number 1. Any questions on this? Sorry. All right, number 2. So number 2 is also pretty straightforward. Essentially what we're looking for is, first of all, the A and the omega of the limit cycle. So we're going to do this graphically. So first, I'm not going to write it out. I'm just going to say, first you want to draw the Bode plot for the linear part. Then you want to find n. So for hysteresis, we showed this in class that the magnitude of n is 4d over tau a, and the phase of that is the arc sine of delta over a. So what we want is essentially we want to draw the Nichols chart, right? So for that we're plotting L and we're plotting -1 over n, right? So the magnitude of that will just be pi a over 4d, and then magnitude of that, this thing, is going to be, because it's negative, we got -180 degrees plus this. So for the first part, pretty straightforward. Draw the Nichols chart, and then find the intersection. Then you'll be able to find omega and a of the limit cycle. So then it asks to, what range of k. I think there's a gain, right? K. What range of k will there not be a limit cycle? From the Nichols chart, you'll see that it goes something. If this is if this is the plot for 1 over n, your Bode plot's going to do something like this, and then there's going to be a range here that if you increase k and shift this up, then you're not going to see a limit cycle. So you just solve for what those are. And then for part C, it wants you to simulate the system and then compare your answers with what you got in part A and B. And so just plot it out in MATLAB. You might see something interesting. Just kind of maybe try to explain why that is. That's all I have to say about that. Number 3. So here we have some compensator. And we have a relay. And then this guy. So the question asks to find a compensator d of s such that the limit cycle that you get has an amplitude at theta of less than 5 degrees. So just write that up. So theta limit cycle is less than 5 degrees. Remember to convert this to radians when you're doing this question. So first of all, we know what the describing function for the ideal relay is. Right? It's just like 4m over pi a. But this a refers to the a that's right here, right? That's entering the nonlinearity. And if I just call this part x, right? To find the magnitude of theta, we have to essentially use the magnitude that's coming here, and we gotta bring that over through this transfer function to theta. So we need the transfer function from x to theta. So we can write that out. Theta over x is 4m over pi a times, let me just do the magnitude, times the magnitude of this thing. Where s equals to j omega limit cycle. Okay. And so when we're in the limit cycle, sorry? So there's two ways to do this. The first way, you could do the feedback, but I mean, if you just consider this part right here, right? Really, you don't need to take into account the feedback, because you could just propagate it forward, right? And you'll end up with this expression. Of course, you could do like, if you wanted to do, x over theta or something like that. Well, first you could invert that, but second you could do like, if this is like theta command, x equals to this d times theta minus theta command minus theta. So going this way is definitely easier in this case. So you just sub this in. Oh, that's right. What is x? The magnitude of x when we're in the limit cycle. That's just 8, right? So if we bring this thing over here, we get the magnitude of theta equals to 4m over pi a. And we could put this in. So these two cancel out. And you just have to solve for this expression is less than 5 degrees. So when you do this, this is a function of omega, right? So you'll end up with something that says, omega has to be greater than some omega min. Okay. And once you have that, you can start doing your Nichols plot, and then figuring out exactly what how much phase, lead, or lag you need. So let me just so for the ideal relay, the native 1/n is going to be along this line. And then the linear part of your system is going to come and do something like this. Why does it start at negative 180 degrees? So in your transfer function, we had this term, right? So this is a pole on the right half plane, and if you remember the stuff from E105, E205, you know, you have a pole here. It starts, you know, if you're going when omega is small, you're at negative 180, and then when omega is big, you know, you're now at negative 90. So that's why this starts at negative 180. So when you do this, you'll realize that, oh well, it doesn't. There's no limit cycle. It doesn't cross, right? So what can you do? Well, we solved for this omega min earlier, right? And let's say it's somewhere over here, right? So it's a function along this line, right? So let's say it's omega min. So just figure out how much of a phase you need. So that you modify this plot so that it does something like this. And you can use whatever E105, E205 techniques to do that. Any questions on that? So once you do this, just simulate your system and then verify your design. All right, good. Number 4, we have a cubic nonlinearity. So the question asks you to find the frequency response of this system. So how do we do that? Well, first let's just write the transfer function from R to Y. Pretty straightforward. Now, I'm going to call this X again. So the entrance to the nonlinearity. So when we try to find the frequency response, typically we're asking for a Bode plot essentially, right? So how you would make a Bode plot is you kind of excite the system at different frequencies and see how it behaves, and then you draw the whole plot. So to do that, we're gonna assume that x takes on the form of a sinusoid. So we have something like a cos omega t, and you could think of this as we're in a limit cycle. So using this, we could find the describing function. So when we do this, we can use the describing function to represent this nonlinearity, which is what it comes down to. And earlier we showed that equals to 3a squared over 4. So our job is essentially to solve for a, given that the input has a magnitude of 1. And to do that, first we need to write the transfer function from r to x. So that is just 1 over 1 plus NL. We could substitute the stuff in. It's 1 over 1 plus 3a squared over 4 over x plus 1 cubed. That gives us evaluate this at x equals to j omega. So again, we're looking for the magnitude of x, which is a, right? So if we take the magnitude of this whole thing, this is just a over 1, right? This is a. And so work out this expression, you'll get something like 1 minus gets just a little bit messy. And then, so from this, we could square everything and just take out these complex numbers. So we can say a squared is just this expression. It's not very pretty. Now what we got to do is basically rearrange this. Move everything on the bottom to the other side, and then you'll get a huge polynomial in terms of A. So if we knew what frequency, if we knew these omegas, right, then it's just a polynomial of A, and we can find the roots of that and solve for A. So the procedure for this is essentially the following. We're going to basically test a bunch of omegas, right? And you're going to do this in MATLAB. You can't do it by hand. We're going to, let me just write that down. So, for each omega, and I tried something like omega from 0.01 to 10 or something like that. Sub it into this polynomial and find roots. So you're gonna get about approximately 6 roots or something, and you're looking for the one that's real and positive. Okay. So once we have this, we know we have the right A. It's right here. And then we can put A into the entire expression for the system and then solve for the frequency response. So we can substitute that A into y over r is NL over 1 over NL. Evaluated that frequency. And we have one data point. So do this for each omega, and then you'll end up with the Bode plots. And just to check your answers, I got something that looked like this. So my magnitude plot looks something like this. And my phase plot looked like this. So it's quite interesting. Any questions on this? Any questions at all? I think that's all I have for today, and went by surprisingly quick. So.
And office hours are tomorrow.
Yes, my office hours are tomorrow from 3:30. Would you like me to extend them? I could extend it to like 5:30 if you want.
Well, I haven't started the homework yet.
Okay, I'll send out an email. It's fine.
The term, what day is it again?
It's currently set for February 21st, I think. Whatever that, I think it's a Thursday. Thursday. Okay. All right.
And it's in class.
Yeah, it'll be in class. Okay, thanks.